Let's talk about the gradient of a function. Let f be a differentiable function at the point x, y, z. The gradient of f at x, y, z is the vector-valued function with an x component given by the partial derivative of f with respect to x. The y component is given by the partial derivative of f with respect to y. And the z component is given by the partial derivative of f with respect to z. That upside down symbol, that symbol that looks like an upside down delta, is called the gradient or del operator. The gradient operator is a vector operator that operates on scalar functions, transforming a scalar function to a vector function that represents the rate and the direction of the fastest increase in the function from the point x, y, z. So when we say it is a vector operator, this gradient operator, as written right now, has nothing to do. It's waiting for a function to operate on. Now that function has to come to this gradient operator from the right-hand side. Otherwise, the gradient operator has nothing to do. It is waiting for a scalar function to transform into a vector function. Suppose we have a function of x, y, and z. That function would be applied to the gradient operator such that the gradient operator would evaluate the partial derivatives of x, y, and z, which will form the x, y, and z components of the gradient function. Now, there's a couple of important properties of the gradient. As long as our function f is differentiable at a point a, b, and let's do this. Suppose f is defined as a function of the independent variables x and y. So this function f, we can also call it z, would form a three-dimensional surface in a rectangular coordinate system. So in this coordinate system, we will have the x-axis coming towards us, the y-axis being the horizontal axis, and the z-axis being vertical. Let's say we have some surface that looks maybe like a hill, kind of like that. Here is our z as a function of x and y. So where we are on this hill is given based off of our coordinates in the x, y plane. So for example, if we're at the point x, y, so we will say, let's take an x value of being right here. Let's take a y value of being right here. This point in the xy plane will correspond to a position on our hill, on our three-dimensional surface, right there. So this point right here corresponds to the point x, y, and z. So if our function is differentiable at that point, and in this case, we'll say x and y is the point with coordinate values a and b. If our function is differentiable at that point, then some properties of the gradient function that we should be aware of. One, the maximum or fastest rate of increase of our function f at ab is equal to the magnitude of the gradient of f, and it's in the direction of the gradient of f at that point. Well, let's look at that. So if we take a look at this hill, you could probably imagine that this hill is probably steepest in this direction. So we'll just draw like a tangent line at that point, representing the steepness of the hill at that point. Well, the gradient operator, if we look at a contour of our hill that passes through that point and project that contour onto the xy plane, the gradient operator tells us the direction that we would have to travel in the xy plane in order to take that path of steepest ascent. The fastest rate of change is the path of steepest ascent. So at that point, projecting down into the xy plane, that would be a point, or that would be a vector that is perpendicular to the point of that, what we'll call the level curve, which is the curve projected into the xy plane. So this right here represents the gradient of our function. That gives the direction that we would have to change our independent variables in order to take the path of fastest increase. Now, since I tried to draw this three-dimensionally, we might have lost, that might not be so clear what I'm talking about. So let's go ahead and look down on the xy plane from the positive z-axis. We're going to take a perspective that is looking down from the positive z-axis. With this perspective, we would have the x-axis going down and the y-axis going to the right. And our hill might look something like that from the top. Now, if you look at where we are on the hill, remember that corresponded to a value of AB for the x and y coordinates. We'll represent that by just coming here. This is our y coordinate, which is B. We will say our x coordinate is A. And here is the point in the xy plane looking down onto our hill. Now, remember, that is sitting on a level curve, and all that level curve means is the value of z is the same everywhere on this level curve. So here's the point A, B in the xy plane. So what does the gradient of our function represent? Well, it represents the direction that we would have to go in the independent plane to have the fastest rate of increase. Now, that direction will always be perpendicular to that level curve at that point. So this right here represents the gradient of f at a, b. And if we were to travel, if we were to change our independent variables in that direction, we would end up ascending our hill at the maximum possible rate. Now we could look at another point on our hill. Let's take a point maybe on the opposite side. So let's take a point right here on our hill, and that point right there has a certain y value and a certain x value. And if we go up, I chose the same level curve, so the actual point on our hill is on the opposite side of the hill. And if we were to be on that opposite side of the hill, the direction that we would have to go to ascend the hill at the maximum possible rate would be a direction perpendicular to the level curve at that point. Now, taking our vantage point, looking down again, the point we just illustrated was this point right here on our surface. And from that point, the gradient evaluated at that point would take us towards the center of our hill. And that gradient is at a right angle to our path. So that is the direction that we would need to change our x and y coordinate in order to ascend the hill at the maximum possible rate. And that maximum possible rate is given by just evaluating the magnitude of the gradient of our function. The second thing you should know is that the maximum rate of decrease of our function at that point is just negative the magnitude of the gradient of our function. In other words, it's in the opposite direction of our gradient. And it's in the opposite direction of the gradient. It has a magnitude equal to the gradient, but the sign in front of our maximum rate of decrease is a negative. And that makes sense, because if we look back at this picture, we could also go down the hill. And if we go down the hill from that point, 180 degrees from our maximum or steepest path, that gives us our steepest decline. And if we were to project down into the xy plane to look at that, well, that would just be a vector that's still perpendicular to our level curve. And this vector right here is equal to minus the gradient of our function. And if we calculate the magnitude of this, negative the magnitude of the gradient of our function is the maximum rate of decrease. At this point AB that we first drew, it would just be in this direction. That's minus the gradient of f. A third property that is very useful to know is that the line tangent to the level curve of our function at the point AB is orthogonal to the gradient of our function, provided that the gradient of our function is not 0. So in this picture, if we look at the point AB and we evaluate the line tangent to the point AB, this line right here, that line is orthogonal to the gradient of our function. In other words, the gradient of a function is always orthogonal to the level curve at a point, where we could measure that orthogonality by looking at the tangent line of the level curve at that point. So if we look at the point we drew on the opposite side of this level curve, a tangent line at that point looks something like this. And the gradient will always be perpendicular to the tangent line of a level curve at a particular point. So you might be wondering, well, why is this important? Well, I've been using the analogy of a hill. Let's continue with that analogy. Suppose we are interested in knowing the rate of change of a function in a particular direction. For example, imagine you're descending into a deep canyon and you want to find the steepest path between 2 points from where you're standing. If you model the canyon where the elevation at any point in the canyon is modeled as a function of x and y, you can evaluate the gradient of that function to determine the direction of steepest ascent or descent from the point at which you're standing. You can visualize that with this model of, well, this is a paraboloid that we call in vector calculus. And this paraboloid is described by the function z equals 4 plus x squared plus 3y squared. If we were to evaluate the gradient of our function at the point 2 and minus 1/2, we would get the direction of steepest ascent. We would get the direction of steepest ascent. And if you were to evaluate the negative of the gradient of our function at that point, you would get the direction of steepest descent. And if you look at the paraboloid on the right, the tangent vectors, which are vectors that lie along the tangent line of the level curve of our function at that particular value of x and y, gives us 0 change in our function. In other words, we just go round and round at the same height in the canyon without ever ascending or descending if we are going in a direction tangent to the level curve. Here's an example of another paraboloid. Now, in this example, it's just really illustrating the direction of greatest ascent, the direction of steepest descent, and the direction of 0 change. So looking at this paraboloid, imagining that this paraboloid represents this canyon that we're descending in, and we'll just choose a different point on the canyon that's a little different than the picture. We'll pick a point right here. And let's go ahead and do our XYZ coordinate system. So we will have the y-axis going to the right, the x-axis coming towards us, and the z-axis being vertical. And we're going to pick a point right here on the surface of our canyon. This corresponds to the value of x equals a, y equals b, and at this point we have a particular value for our z coordinate. Z is equal to f at a and b. So looking at all values of z equivalent to that, that would take us on a path around our paraboloid. So this path, all values of z are the same. This is what we call a level curve because we're not increasing in our value of z and we're not decreasing in our value of z. So a point on this path is described by 3 coordinates, an x coordinate, a y coordinate, and a z coordinate. And so this point here that we first drew would be the point A, B, and our function evaluated at A and B. Well, at that point, you could see that for us to descend, we would have to be going towards the center of our valley. So that center of the valley would mean that if we were to project our level curve into the xy plane, when we project that level curve into the xy plane, we see that if we were to evaluate the gradient of f at the point AB, that gradient being perpendicular to the level curve tells us the direction in which we would have our fastest descent in this situation. So in this situation, if we are going into the curve, that's going to be our fastest descent. This would be minus the gradient of our function. while the direction of steepest ascent, going up, climbing up out of the valley, or is given as the gradient of our function. So the gradient of our function tells us the direction we would need to change and how we would need to change our independent variables x and y in order to increase our value of z at the fastest possible rate. And the negative of the gradient of our function tells us the direction we would need to change x and y to have the fastest possible descent.